The air is cool and faintly mineral in the POSTOJNA Caves, and somewhere above you water gathers on limestone. It pauses at the ceiling in a small clear bead, held there by surface tension and time. Around you, the chamber is dim, pale calcite, catching only the softest suggestion of light. Nothing here seems to move, yet the cave is full of slow motion. Rain has passed through forest soil, through cracks in the Dinaric Karst, carrying dissolved limestone into the dark. When each drop reaches the open air, it releases a little carbon dioxide and leaves a trace of calcite behind. Over years, that trace becomes a hollow straw, then a stalactite, then perhaps a stalagmite rising from below. The Pivka River has carved the larger passages, but these quiet forms grow by a smaller rhythm. For now, we stay with one drop and follow how stone is made almost too slowly to see. The first change is small enough to miss, unless you decide to wait for it. A bead of water swells on the cave roof, bright at its lower edge and heavier than it was a moment ago. It does not hurry, because nothing in this chamber has ever needed to hurry, but its weight is increasing, and that quiet increase is the beginning of movement. You could follow the wide passage, where the Pivka River once opened long corridors through the limestone. You could look across the chamber, at pale columns and folded curtains of calcite, already finished enough to feel ancient. But we choose a narrower path. We choose this one drop because its smallness makes the cave easier to understand. It gathers above you, at a tiny point in the ceiling where water has found a crack. That crack is not random. It belongs to the structure of the limestone itself, to bedding planes, joints, and older lines of weakness. Long before this drop appeared, water had already chosen this route many times. Each arrival made the route a little more dependable, not by widening it suddenly, but by returning to it. Because the water returns, the ceiling point becomes important. Because the ceiling point becomes important, the cave begins to build downward from almost nothing. This is the quiet escalation here. Not a collapse, not a flood, not any loud event, but a repeated arrival at the same place. In POSTOJNA, the large spaces tell one story, carved by moving water over long spans of time. The Speleothems tell another story, written after the rooms were opened, when dripping water began to give stone back. The walls around you are limestone, made mostly of calcium carbonate, formed from ancient marine material before this land ever became karst. That older sea is gone now, lifted and folded into southwestern Slovenia, exposed to rain, roots, and cold air. Yet the cave still carries a memory of water in every surface. The coolness stays near constant, usually close to the average temperature of the ground above. The air feels still, but it exchanges slowly with the outside, through entrances, cracks, and the larger river passages. That matters, because cave air changes how water behaves. A drop that was hidden in stone can hold more dissolved material than a drop exposed to open cave air. So when it reaches this chamber, something subtle begins. It starts to release a little carbon dioxide, the gas that helped it dissolve limestone in the first place. As carbon dioxide leaves the drop, the balance shifts. The water can no longer carry quite as much calcium carbonate. A tiny trace of calcite is left at the edge of the opening. That trace may be thinner than a breath, but it is real. It is the first possible ring of a formation. The chamber seems unchanged. Your eyes would not detect it. Even if you came back tomorrow, the ceiling would look the same. But the process has already crossed a line. Once a film of calcite forms at the drip point, the next drop has a surface to continue. The cave has made a beginning, and beginnings in limestone do not need to be large. They only need to be repeated. The drip finally releases. It falls through the dim air, a short silver line, then disappears into sound. The sound is slight, a single tap on stone below. In a quiet cave, that tap feels almost intimate. It tells you there is a floor beneath the darkness, and that the ceiling and floor are already in conversation. But before we follow the drop downward, we have to understand what it carries. So we let the chamber remain around us, cool and patient, while the mind moves upward through the ceiling. We pass into the rock above POSTOJNA, not quickly, but the way water does. There are no open rooms at first. There are only fine spaces, narrow cracks, dark seams, and places where limestone touches limestone. Above that stone, there is forest soil. Rain arrives there softly, in winter, in spring, during long damp weather that soaks into leaves and roots. At the surface, rainwater is already slightly reactive because it has met carbon dioxide in the air, but in the soil, it meets much more. Roots breathe, microorganisms break down fallen leaves, organic matter darkens and softens, and the spaces between soil grains hold carbon dioxide-rich air. As the rain moves through this living layer, it absorbs that gas. The water becomes weak, carbonic acid. The word acid may sound sharp, but here it is gentle. It is not violent. It is patient enough to matter. Carbonic acid is what forms when water and CO2 combine, and in karst landscapes it is one of the great quiet makers. It finds limestone, and over time it dissolves a little of it. The limestone is calcium carbonate. When carbonic acid touches it, some of that solid stone becomes dissolved calcium bicarbonate in the moving water. Nothing looks dramatic at the scale of a single raindrop. But rain does not fall only once. Season after season, water sinks through soil and enters fractures in the Dinaric karst. The Dinaric karst stretches through this region as a landscape of sinkholes, disappearing streams, caves, springs, and hidden drainage. POSTOJNA is part of that larger pattern. On the surface, the ground may appear wooded and still. Below, water is arranging itself through stone. The Pivka River is one expression of that arrangement. It disappears underground, travels through carved passages and helps shape the known cave system, but the drop we follow is not the river. It is smaller, higher, slower. It has seeped through limestone above the chamber, picking up dissolved minerals in darkness. At each narrow contact, it has changed slightly. It may pause in a pore space for hours. It may slide along a bedding plane for days. It may wait in a thin fracture until more water from above presses gently behind it. This hidden delay is part of the formation. A speleothem does not begin when the drop becomes visible. It begins earlier, when rainwater becomes chemically ready to return stone to the cave. Because the water has moved through soil, it carries carbon dioxide. Because it carries carbon dioxide, it can dissolve limestone. Because it dissolves limestone, it arrives at the cave roof with calcium and bicarbonate in solution. Then, because the cave air is different from the enclosed fracture, the drop begins to lose CO2. The cause is quiet, but the consequence is visible over time. Calcite precipitates. Stone appears from water. This is not magic, though it can feel that way in the dimness. It is chemistry behaving slowly enough to become landscape. Back in the chamber, the drop point waits for the next bead. There may be a thin, wet sheen around it, a tiny darkening on the ceiling. There may be no shape yet, only a place where water prefers to emerge. The decision to stay with it changes how the cave feels. Instead of seeing finished formations as silent objects, you begin to see them as actions still taking place. A stalactite is not simply hanging, it is receiving. A stalagmite is not simply standing, it is answering. Flowstone is not simply draped over rock, it is water remembering the slope. The whole chamber becomes less like a room and more like a set of slow events. Some events are centuries old. Some began this season. Some have not yet become large enough to be named. The ceiling above you is uneven, pale in some places, shadowed in others. Where calcite is clean, it may catch a creamy glow. Where moisture gathers, it may look darker, almost polished. Where old clay has stained the surface, warm browns and muted reds may appear. These colors come from small differences in minerals, from iron oxides, from sediment, from water paths that were never quite identical. The cave is not empty stone, it is a record of separate movements laid over one another. The river made the broad void, the dripping water makes the fine architecture. The air helps decide where mineral stays, the temperature holds the pace steady, and time gathers everything into forms your eyes can finally recognize. Another drop appears. It swells from the same point, clearer than the rock around it. For a moment, it reflects a tiny, inverted version of the chamber. Then it lengthens. This second drop carries nearly the same ingredients as the first, but not exactly. Perhaps the rain above was more recent. Perhaps soil carbon dioxide was higher after a warm, damp week. Perhaps the water passed through a slightly different thread of limestone. These small differences can alter how much calcite is left behind. They can change growth by a fraction. A fraction repeated enough times becomes shape. This is why speleothems are never merely decorations. They are local outcomes. Each one depends on a particular path from the surface to the cave. Move the drip a little and the form changes. Change the ventilation and the chemistry changes. Change the flow rate and the texture changes. The first trace of calcite at the ceiling may begin as a ring around the opening. That ring forms because the edge of the hanging drop is where water, air, and stone meet most delicately. CO2 escapes there. Calcite begins to deposit there. The center remains open because water keeps passing through. If the path remains steady, a hollow tube can grow downward. This is often called a soda straw stalactite. The name is simple, but the form is precise. It is a thin calcite tube, sometimes only a few millimeters wide, with water moving through its central channel. Each drop arrives through the hollow center. Each drop leaves a little calcite at the rim. The tube extends downward, ring by ring, as if the cave is drawing a line in the air. Growth can be slow. In some caves, it may be a fraction of a millimeter each year. In others, where drip rates and chemistry are favorable, it can be several millimeters in a year. POSTOJNA, like other active karst caves, contains many forms shaped by these balances. There is no single pace for every formation. Each one has its own supply, its own chemistry, its own exposure to air. That is why the cave feels so varied. One ceiling point may build a delicate straw, another may thicken into a broader stalactite. A sloping wall may receive water as a sheet and become flowstone. A floor patch may swell into a rounded mound. The same ingredients can make different shapes because the movement changes. The drop falls again. The sound is quiet, but now it carries meaning. It tells us that not all mineral has been left at the ceiling. Some remains in the falling water. When the drop strikes below, it may spread outward in a tiny splash. It may release more carbon dioxide. It may leave calcite on the floor. At first, that floor deposit is no more visible than the ceiling ring. But if the drops keep landing in the same place, the floor begins to answer. This answer is the beginning of a stalagmite. It grows upward, not because it reaches, but because every drop leaves a little behind. Ceiling and floor are now linked by falling water. The distance between them becomes part of the form. If the drop falls from a greater height, it may splash more widely. A wider splash can make a broader mound. If the drop falls gently from a shorter height, the deposit may be narrower. If evaporation is limited, if air is calm, if the water stays evenly saturated, the surface may grow smooth and rounded. If flow changes seasonally, thin layers may stack in subtle bands. The cave is adjusting its shapes to conditions no human hand has arranged. The stakes remain quiet, but they are real. If the drip shifts, the straw may stop growing. If the crack clogs with calcite, water may find a new opening nearby. If the cave air changes, mineral may deposit more quickly or more slowly. A formation that seems inevitable is actually dependent on a chain of small continuities. The water must keep arriving, the path must remain open, the chemistry must stay within a range that allows calcite to return. The cave does not force this, it only receives what the surface sends. Above, rain falls through forest and soil. Below, calcite gathers in darkness. Between them, the karst carries messages slowly. The Pivka River, moving through the larger cave system, is a different kind of message. It speaks in carved passages, sediment banks, scalloped rock, and the memory of flowing current. The river helped hollow the spaces where the speleothems could later grow. Without the river and earlier underground drainage, there would be no chamber open enough for drops to fall through air. But without the later dripping, the chamber would remain less ornamented, less layered, less full of vertical time. The river removes stone, the speleothem returns it. One process opens the dark. The other fills it with pale forms. This balance gives POSTOJNA its particular calm. The cave is not frozen, it is moving in opposite ways at once. Water dissolves limestone above. Water deposits calcite below. A passage carved by flow becomes a room where stillness can build. The result is a landscape that seems motionless only because its motion is longer than attention. You stand or sit, or simply imagine yourself near the damp floor. The air is cool against the skin. Sound travels softly, then fades. A drop falls somewhere to the left. Another answers farther away. These sounds are not regular like a clock, but they create a sense of time, not human time, cave time. In that slower measure, a year may pass without changing what the eye believes it sees. But the water knows the difference, because it has crossed the ceiling again and again. The first calcite ring becomes a tiny lip, almost as delicate as dried milk at the rim of a cup. It is pale, circular, and fragile, but it gives the next drop an edge to follow. The drop does not spread randomly now, because the forming rim guides its contact with the air. A little tube begins to take shape, and the center stays open. This is the important reveal hidden in the quiet ceiling. The stalactite does not begin as a solid cone, but as a hollow straw. Water moves through the middle, and calcite gathers mostly around the rim. Each bead arrives from the same narrow route, pauses at the lower edge, and then lets go. While it pauses, carbon dioxide escapes from the water into the cave air. As that gas leaves, the dissolved calcium bicarbonate can no longer remain fully dissolved. A little calcium carbonate returns to solid form as calcite and attaches to what is already there. The tube lengthens by the thickness of many almost invisible edges. It is not carved downward. It is assembled downward. This distinction matters because the cave is doing two opposite things in one continuous system. Above the chamber, carbonic acid water dissolves limestone, widening its secret paths through the rock. Inside the chamber, the same water loses carbon dioxide and gives some limestone back as calcite. The stone is being moved, not created from nothing. It is borrowed from one place, carried in solution, and returned in another. That return is slow enough to feel like stillness, yet it is precise enough to build a hollow tube that may remain open for centuries. The soda straw grows best when the drip stays gentle and dependable. If too much water arrives, the drop may run along the outside instead of through the center. If too little water arrives, the rim may dry and growth may pause. If grains of clay or tiny crystals clog the hollow channel, the water must choose another route. Then the straw may stop lengthening as a tube and begin thickening on the outside. A delicate form can become a heavier stalactite, not because it failed, but because its water path changed. In POSTOJNA, many such changes are written into the cave's pale architecture. Some forms look thin and glassy, like suspended reeds. Others are rounded, ribbed, or heavy with older layers of mineral flow. All of them began with water finding a way through limestone. All of them depend on the small conversation between water and air. You can imagine placing your attention on the end of the growing straw. It hangs only a short distance from the ceiling now, perhaps no longer than a fingertip. The tip is wet, brighter than the dry calcite above it. A bead forms there, swelling downward in the calm air. For a while, the bead is part of the straw, held by surface tension. Then its weight overcomes that hold, and it separates. The fall is brief, but it changes the lower chamber. The drop strikes the floor beneath, and for an instant, water spreads outward in a thin, clear skin. Some of it splashes in a circle too small to notice from a distance. Some of it lingers in a shallow depression on the limestone floor. Some of it seeps into sediment, if sediment lies there, or follows a tiny slope away. But before it leaves, more carbon dioxide escapes. More calcite may precipitate. The floor receives what the ceiling did not keep. At first, the deposit is nothing more than a faint roughness. It may look like a pale speck, or no visible change at all, but the drop returns, then another returns. A season passes, and the landing point remains damp more often than its surroundings. The stone there grows a thin mineral skin. That skin thickens layer by layer until the floor begins to rise. This is the beginning of a stalagmite, the upward answer to the ceiling's slow descent. It does not stretch toward the straw in any living sense. It simply receives the falling water. But because the water falls in one place, the mineral gathers in one place, and because the mineral gathers, the floor's shape changes. The first shape is often a low mound, rounded by repeated impact and spreading droplets. The mound may have a smooth top if the drip is regular and the water chemistry steady. It may have a rougher surface if flow varies, or if tiny impurities interrupt crystal growth. It may widen if falling drops splash outward from a higher ceiling. It may grow more narrowly if the falling distance is short and the drip remains centered. Height matters, because a long fall lets the drop strike with more spread. But even this impact is quiet. There is no forceful blow, only a soft tap repeated beyond counting. The cave floor records that repetition in calcite. The stalagmites' early layers may be slightly cloudy, because water arrives with tiny particles from the root above. At other times, the calcite may grow clearer, forming crystals that transmit a little light. Trace minerals may tint the deposit cream, honey, grey, or faintly reddish brown. Iron can warm the color. Clay can soften the clarity. Organic traces from soil can leave subtle tones that only appear when the surface is freshly broken or closely studied. From where you are, in the dim chamber, the growing mound is simply pale and still. It belongs to the floor now. It has become part of the cave's furniture of time, yet it remains connected to the ceiling by each falling drop. This is the first vertical relationship in the chamber, and it has consequences. The straw above grows longer, adding calcite around its hollow tip. The stalagmite below grows higher, spreading calcite where droplets land. Between them, open air holds the distance. That distance is not empty. It is the place where water falls, loses gas, divides, and leaves memory. If the drip line remains steady, ceiling and floor keep answering one another. If the line shifts slightly, the floor mound may become asymmetrical. One side may grow faster, because more water reaches it. A small ridge may form where splash consistently travels. A hollow may remain dry, because droplets no longer reach it. The shape records the discipline, or the wandering of the water path above. This is why speleothems are evidence, not ornament alone. They tell whether conditions stayed stable. They show where water moved. They preserve hints of airflow, saturation, and seasonal recharge. The cave is not speaking loudly, but it is speaking in surfaces. Every rounded edge means something happened often enough to matter. Every rib, ledge, and band marks a slight change in how water arrived. If you look carefully at a mature stalagmite, you may see broad growth rings on its surface. They are not the same as tree rings, but the comparison can help the mind slow down. A tree adds wood as it lives in sunlight and air. A stalagmite adds calcite as water passes through darkness. Both grow by increments. Both hold traces of weather. Both become records because they cannot move away from the place that feeds them. The stalagmite beneath the straw begins to widen at its base. Its top remains wetter because the drip keeps landing there. Water runs from the top down the sides in a thin film. As it travels, it may deposit more calcite along the slope of the mound. That makes the sides smoother and sometimes gives the surface a softly polished look. The mound is becoming a form with internal order. It has a drip point, a top, a spreading surface, and a growing base. If the drip remains strong, the top may develop a small cup or shallow depression. Water can pool there briefly, losing carbon dioxide before spilling over. If the drip weakens, the top may dry between arrivals, and crystals may grow differently. These small differences do not make the cave dramatic. They make it exact. A few more carbon dioxide molecules in the water can change the amount of calcite deposited. A slight shift in cave ventilation can change how quickly that gas escapes. A warmer or cooler period above can alter soil activity, root breathing, and the amount of CO2 available. A wet year can flush more water through the fractures. A dry year can slow the drip until the ceiling rests almost without sound. The stalagmite below holds these variations, not as memories with words, but as layers. The layer from a wetter period may be thicker. The layer from a drier period may be thinner, denser, or interrupted. A change in vegetation above may alter carbon chemistry. A change in the water's route may introduce different trace elements from another part of the limestone. Nothing needs to happen suddenly. The record forms because the system continues. This is part of the patience of POSTOJNA's underground world. The cave has rooms shaped by the ancient work of the Pivka River. It has passages where water once moved with more volume through limestone. It has chambers where flowing water left scallops, sediments, and open space Then, after those spaces became air-filled enough for dripping, another kind of water began working. Not the river current, not the broad underground stream, but seepage, descending from soil and rock, drop by drop. This later water brought the cave its vertical architecture. The river carved the hall, the drip furnished it with time. You remain near the same growing pair, because following one pair keeps the whole process close. The ceiling straw is longer now in imagination. The floor mound has risen slightly, though perhaps only by a few millimeters, over many years. The two are still far apart. Most of the chamber remains open between them, but the relationship is established. Each drop carries the ceiling's chemistry to the floor. Each fall links the upper fracture to the lower deposit. If you could return after a century, the difference might still be modest. The straw might be longer by a few centimeters if conditions favored growth. The stalagmite might be broader, or higher, or subtly layered, but the cave would not present the change as an event. It would simply be there, as if it had always been so. This is one of the gentle difficulties of understanding Speleothems. Their growth asks the mind to accept very small causes over very long intervals. The visible form is only the final accumulation of invisible decisions. A drop hangs, a little gas escapes, a little mineral stays, then the drop falls. Again, again, again. The repetition is not mechanical because each drop belongs to weather above. During snowmelt, water may move differently through the karst. During a long rain, fractures may fill and connect, delivering more frequent drips. During dry months, the route may narrow to occasional beads. After warm periods, soil CO2 may be higher because roots and microbes are more active. After cold periods, the water chemistry may shift again. The cave receives all of this without needing to know it. It records the surface from below. The forest above POSTOJNA is part of the Speleothem. Even though it never enters the chamber whole, leaves fall and decay. Roots respire in the dark soil. Microorganisms transform organic matter. Rain carries the chemical result downward. The limestone receives that water into cracks and bedding planes. The cave air releases the carried gas. Calcite settles out, slowly, into forms that look separate from the forest. But the separation is an illusion. The stalactite is connected to rain. The stalagmite is connected to roots. The column, if it ever forms, will be connected to seasons that passed overhead unseen. This makes the chamber feel less enclosed. Even deep underground, it is part of a larger breathing landscape. The breathing is slow and mostly chemical. CO2 builds in soil, water absorbs it, limestone dissolves. Cave air receives the gas back, calcite appears. The cycle does not close perfectly, because some water moves on and some mineral is carried elsewhere. But enough returns here to shape the darkness. At the tip of the straw, the next bead begins. It may seem identical to the previous bead, yet no two are exactly the same. One might carry a little more dissolved calcium. Another might spend longer exposed to cave air before falling. Another might arrive after water has flushed a new microchannel above. These differences are small enough to vanish in the moment. Over centuries, they give the formation texture. A stalactite that begins as a hollow straw may keep its thin form for a long time. If the central channel remains open, water continues to move down through it. The tube can grow longer and remain delicate. Some soda straws in caves are astonishingly slender, like pale threads suspended from the roof. They can look fragile because they are fragile. But their fragility is not weakness in the landscape. It is evidence of a steady, gentle drip, undisturbed enough to keep a narrow path alive. If the hollow tube breaks naturally, or clogs, water spills over the outside, then calcite begins coating the exterior. The once thin straw becomes the core of a thicker stalactite. Layers wrap around it. The shape grows heavier, more conical, sometimes tapering like a candle made of stone. You can imagine the old straw still hidden inside, a narrow memory at the center. It is the first line of growth, preserved within later calcite. Many mature stalactites carry such hidden beginnings. Their outer form may be broad and solid. Their origin may have been a tiny ring around a waterhole. The cave often hides its beginnings inside its completed shapes. The floor does something similar. A large stalagmite may contain a small original mound at its center. Later layers wrap over it. New flows smooth old irregularities. A change in drip position may shift the growth axis, making the interior lean slightly through time. If scientists cut or core a small sample carefully and with restraint, they may see these changes in cross-section. But in the sleeping chamber of the imagination, we do not disturb the stone. We simply understand that inside the pale form, time is layered. The outside is present, the inside is earlier rain. The stalagmite continues to swell beneath the drip. Its upper surface becomes the place where each falling drop breaks. The impact releases dissolved gas faster than a quiet pool might. Tiny splashes move outward, and each splash can leave a fringe of calcite. If the splash zone remains wide, the stalagmite may become broad and low. If the falling drop stays centered and gentle, the form may rise more like a rounded pillar. In some caves, rapid dripping can produce rough, knobby surfaces. In others, steady, slow dripping produces smoother domes. The difference is not decoration. It is water behavior made visible. POSTOJNA's chambers hold many variations because the cave system is large and varied. Air does not behave the same in every passage. Water does not reach every ceiling point by the same route. Some areas are closer to active river influence. Some are drier, higher, or more insulated. Some surfaces receive only faint seepage. Others carry regular drips through much of the year. This variation gives the cave its richness. It is one system, but it has many local climates. A few meters can change the shape of a speleothem. A small draft can increase carbon dioxide loss and encourage deposition. A still pocket of humid air can slow evaporation and alter crystal growth. A slanted ceiling can send water sideways before it falls. A rough floor can divide splashes into several directions. All of these details matter because calcite responds to conditions at the surface where it forms. Crystal by crystal, it adapts to the moment. The cave does not plan, but its forms are full of consequence. Now the growing pear has aged in the mind. Perhaps many centuries have passed in this quiet attention. The soda straw has thickened into a more solid stalactite. Its outer surface is damp in places, with fine ridges where water has run. The stalagmite below is no longer only a low mound. It rises clearly from the floor, rounded and pale, with a base that spreads into the surrounding calcite. The open gap between them is smaller than before. Still, it remains open. Drops fall through it, one at a time. For a long span, this is the shape of the relationship. The ceiling grows downward, the floor grows upward. Water crosses the air, and the two forms remain separate. This separation may last longer than many surface forests. It may last through changes in vegetation, climate, and river level. It may last while other drip points nearby begin, pause, and begin again. A formation that will someday become a column must first remain loyal to its route. The drip must not wander too far. The fracture above must stay open enough. The cave air must allow deposition. The floor must remain in place, not eroded away by renewed strong flow. All of these conditions must hold, not perfectly, but sufficiently. This is why a column is more than a joined shape. It is evidence of long stability. It means the ceiling and floor had time to meet. In POSTOJNA's larger chambers, columns can stand like pale supports, though they do not hold the cave up in the way built pillars do. They may touch roof and floor, but their meaning is geological, not architectural. They mark an old drip path that closed the distance. They show where air once carried falling water between two growing surfaces. They also change what happens after they form. Before contact, drops fall. After contact, water clings, slides, and spreads. This change is approaching now, but it does not arrive with drama. The final gap grows smaller through many repeated deposits. A drop leaving the stalactite tip has less distance to fall. It strikes the stalagmite top with less spread. The splash zone narrows. More water stays close to the center. Calcite begins to build faster along the axis between them, if the chemistry remains favorable. The stalagmite top may become sharper or more elevated. The stalactite tip may broaden. The air between them becomes a small dark space, crossed by every drop. You could place a hand near it in imagination, not touching, simply sensing the cool wetness. The cave would feel unchanged, yet the geometry has altered. The falling water no longer has enough room to behave as it once did. It leaves the stalactite, but almost immediately meets the rising top below. The sound changes first, though the change is very slight. The tap becomes softer, less separate from the wet stone around it. A drop that once fell freely now breaks almost at once and spreads across the stalagmite's upper surface. Some of the water climbs the side by surface tension, holding briefly to the damp calcite before sliding down again. The space between roof and floor has become a narrow passage for water. It is still open air, but only just. The stalactite and stalagmite remain separate forms, yet their growth is now focused toward the same small darkness. This is the period when the cave seems to be waiting, though nothing here waits in a human way. It only continues. The drip continues. The release of CO2 continues. The quiet return of calcium carbonate continues. Each drop leaves a little more calcite on the lower tip above and on the rounded summit below. The old distance is being erased by almost invisible additions. The closer the two forms come, the more strongly they influence each other. The stalagmite catches the water before it can splash outward. The stalactite receives damp air rising from the wet surface below. Between them, the humidity is high, the gap is narrow, and the water film lasts longer. These conditions can encourage calcite to gather near the meeting point. Not always quickly, not always evenly, but steadily enough. If the drip remains faithful, the cave is now making a decision without intention. Either the drip will shift before contact, and the two forms will remain apart, or the path will hold, and the ceiling and floor will meet. For a long time, both futures remain possible. A tiny obstruction in the crack above could change everything. A grain of clay, carried from the soil, could lodge in the narrow channel. A seasonal change could send more water along the outside of the stalactite. A new microfracture could open nearby, stealing part of the flow. The column is not guaranteed. Its making depends on the continued agreement of rain, soil, limestone, air, and time. This is why the moment of joining is quiet, but important. It means the system did not wander too far. It means enough water returned to the same line again and again. It means the cave kept the same small promise for centuries, perhaps longer. Now the final gap is no wider than a fingertip, then thinner than that. A drop gathers at the stalactite's lower edge, but it does not fall cleanly. It stretches downward, touches the damp top of the stalagmite, and becomes a narrow bridge of water. For a moment, liquid connects the two calcite bodies before gravity draws it over the surface below. At that instant, the old falling path has nearly ended. There is still air around the water, but the behavior has changed. The drop is no longer simply released, it is guided. It clings from upper stone to lower stone, as if the cave has drawn a wet thread between them. Calcite begins to deposit along that thread's contact points. A little mineral gathers where water lingers. A little more gathers where CO2 escapes. The gap becomes smaller by the thickness of many thin skins. Then, one season, or one wet year, or one long series of ordinary drips, the last open space closes. The stalactite and the stalagmite meet. There is no sound to mark it. No sudden change passes through the chamber. The column forms in the same quiet voice that made the straw, the mound, and the narrowing gap. One surface touches another. Calcite seals the contact. The ceiling and floor are joined by stone. The old air path is gone. The falling drop is gone. Water now travels along a continuous body, sliding from the ceiling down the column's surface. This is an irreversible turn in the local story. The cave has not ended anything, but one kind of motion has been transformed. Before the joining, water crossed open space. After the joining, water follows stone. It runs in thin films, sometimes along grooves, sometimes around subtle ridges. The column becomes a new path. It is no longer only a record of past dripping. It is now an active surface, receiving water and redistributing it. The upper part may remain wetter on one side, depending on how the feeder crack supplies it. The lower part may develop narrow ribs, where water repeatedly descends. At the base, water can spread outward and begin coating the floor nearby. The column changes its own neighborhood. A drip that once built a single vertical pair may now feed flowstone at the base. A film that once fell as drops may creep along a ledge, Mineral deposition shifts from a point to a surface. The cave's architecture becomes more connected. This is one of the quiet consequences of completion. A column looks like an endpoint, but for the water, it is a new route. Its surface offers length, texture, and contact with cave air. As water slides along it, CO2 continues to leave solution. Calcite continues to precipitate. The column thickens, not only where it first joined, but along its sides. Old tapering forms softened under later coatings. A thin stalactite and a separate stalagmite become hidden inside a heavier, smoother body. Their meeting place may be buried beneath later mineral layers. The first contact, so important to the story, may become invisible. The cave often does this. It keeps the cause, but hides the scene. From a distance, the mature column may seem like one continuous pillar that has always stood there. But inside, it remembers two directions of growth: downward from the ceiling, upward from the floor. Then inward, across the final gap, then outward, as water spread along the joined surface. A column is a history of changing water behavior. It tells of long stability, but not perfect stillness. It tells of a drip that persisted, then altered itself by completing its own path. The air around the column is the same cool cave air, but the local moisture has been rearranged. Where droplets once fell, the floor may be quieter. Where water now runs off the column, new wet patches appear. Small beads may gather at the base, lingering on sloped calcite before moving away. Those beads carry remaining dissolved minerals. They may begin to coat older sediment. They may fill tiny hollows in the floor. They may join other films of water moving downslope toward lower parts of the chamber. In POSTOJNA, this local shifting happens within a larger karst system that is always responding to surface water. Rainfall above changes the drip rate. The Pivka River influences humidity, airflow, sediment, and the shape of the larger passages. Cave entrances and unseen cracks allow slow exchange with outside air. Even when a chamber feels sealed, it is not separate from the landscape above it. It breathes through stone, river corridors, and fractures. That breathing is subtle. It may strengthen in colder seasons when outside and inside temperatures differ more. It may soften when the air outside is closer to the cave's own constant coolness. It may affect how quickly CO2 leaves dripping water. It may change where calcite grows most readily. The column, standing in that quiet exchange, becomes a surface where chemistry meets air again and again. Its growth rate may slow after joining, or it may thicken in places if films of water continue to flow over it. The exact result depends on the balance of supply, saturation, ventilation, and contact time. A thin, fast runnel may deposit calcite differently from a broad, slow film. A wet surface that remains humid may build smooth layers. A surface exposed to slightly more airflow may lose CO2 more readily and accumulate mineral in ridges. You can see this in the way calcite surfaces rarely grow as perfect geometry. They lean, they bulge, they carry soft shelves, ripples, and seams. The cave writes in water paths, not in straight lines. The column side may develop faint vertical grooves, each one marking a preferred descent of water. A ridge may rise between two grooves where mineral gathered along an edge. A bulge may form where a persistent film slowed and spread. At the base, flowing water may fan outward over the floor, making a pale apron. This apron is the beginning of another kind of speleothem. Not a hanging straw, not an upward mound, not a joined column. It is flowstone. Flowstone begins where water moves as a sheet or film across a surface. It may coat walls, floors, slopes, and older broken rock. It may look as if the cave has poured cream over stone and let it harden in place. But there was no single pour. There were countless thin movements. Water slid, paused, released CO2, and left calcite behind. Then more water followed. Layer after layer, the surface changed. Flowstone can smooth rough limestone into soft, rounded shapes. It can cover angular rock with pale mineral skin. It can bury older textures, leaving only a flowing outline. At times, it can preserve the memory of motion more clearly than the rock beneath. The surface may ripple like frozen water. It may form terraces, rims, and small basins if water pools briefly along its path. It may hang in folds where it develops along a sloping wall. The difference between a stalactite and flowstone is mostly the difference between falling and sliding. A drop falling through open air builds points and mounds. A film sliding over a surface builds sheets, ribs, and draperies. The chemistry is related. The movement is different. The form follows the movement. After the column closes the old distance, more water may travel along its side and onto a sloped floor. There, the drip's influence spreads. The cave no longer builds only a vertical line. It begins to grow sideways. Water leaves the column and reaches a low incline of limestone. It thins into a film, clear and nearly silent. Because it is spread out, more of its surface touches cave air. CO2 can escape along the entire wet sheen. Calcite begins to deposit across the slope. At first, this coating is only a faint brightness on the rock. It may make the surface look freshly washed. Then, over many wet seasons, it thickens into a visible skin. The rock beneath becomes less distinct. Edges soften, small pits fill. The slope grows pale and smoother. If the film follows the same line repeatedly, a raised rib may form along its margins. If water pools behind tiny rims, it can build shallow steps. These steps are called limestone dams when they become distinct enough. In a cave like POSTOJNA, where water supply varies through the year, such surfaces can grow unevenly. A spring recharge may bring frequent films. A dry period may leave surfaces damp only in patches. Snowmelt can feed slow seepage through fractures above. Warm months can change soil CO2 and alter the water's chemistry. The cave receives all of it as thin layers. The flowstone does not grow in one smooth act. It grows in pulses, pauses, and returns. Yet from a distance, those many returns become a single continuous drape of calcite. This is how the cave softens itself. The river once cut passages through limestone with moving water and sediment. Later, dripping and flowing mineral water lined those passages with pale forms. The contrast is gentle but deep. The river opened voids. The Speleothems rounded them. The river made space. The drips made memory visible. Near the joined column, the flowstone apron may overlap older floor deposits. It may partly cover small pebbles left by previous water movement. It may seal fine sediment beneath a translucent layer of calcite. It may preserve a surface that would otherwise shift. The cave is always selecting what remains exposed and what becomes hidden. A ridge of old mud may disappear beneath mineral. A shallow groove may be emphasized by repeated water flow. A small fallen fragment may become coated until it seems grown from the floor. This is not concealment in any deliberate sense. It is simply deposition. Water carries stone in solution. Air changes the balance. Stone returns. The returning stone covers what is there. In some places, flowstone grows so smoothly that it resembles wax. In others, it becomes wrinkled, ribbed, or scalloped by the path of water. Where the slope is steep, thin films may draw long vertical streaks. Where the slope is shallow, water may spread and pool. Where a ledge projects, water may drip from its lower edge, beginning new small stalactites below. One form leads to another. A column feeds flowstone. Flowstone reaches a lip and begins dripping. A drip builds a new stalactite. A floor beneath begins answering. The cave is a network of slow consequences. No formation is entirely alone. Even the single drop we followed belongs to many paths. It began in soil. It moved through limestone. It built a straw. It fed a stalagmite. It closed into a column. Now it spreads along the side and floor, becoming part of flowstone. At each stage, the water's motion changed. At each stage, the same chemistry found a new expression. This is why speleothems are so varied, even when they are made mostly of calcite. The mineral may be the same. The shape is the history of movement. On a sloping wall near the column, water does not fall straight down. It clings to the rock. It follows gravity, but gravity is guided by texture. A slight ridge turns the film left. A shallow groove gathers it into a line. A rough patch slows it. A smooth patch lets it spread thin. The cave wall becomes a map of tiny decisions. Over time, those decisions deepen. Where more water flows, more calcite may accumulate. Where calcite accumulates, the surface shape changes. Where the surface changes, future water takes a slightly different path. The formation influences its own next layer. This feedback is quiet but important. It helps explain why flowstone develops ripples and folds instead of remaining flat. A small unevenness becomes a preferred path. A preferred path receives more water deposits more mineral. The unevenness grows into a visible ridge. The cave's surfaces are shaped by repetition, and repetition is never perfectly uniform. If the wall tilts outward, water may hang for a moment along a lower edge. There, it can deposit a thin line of calcite. If that line extends downward and outward, it may begin forming a curtain. A curtain is a sheet-like speleothem that grows from water flowing along an inclined ceiling or wall. Instead of dripping from one point, the water travels along a line. Calcite deposits along that line, lengthening a thin sheet into the air. The sheet may be translucent when young. Light passing through it may reveal warm bands of cream, amber, or brown. In the dimness of the cave, it can look like folded fabric, but it is stone. It is a slow mineral edge, drawn by water moving along a slant. These curtains, also called draperies, are among the most delicate-looking forms in caves. They show how a small shift in the path of water changes the entire geometry of growth. A vertical drip makes a straw. A falling drop makes a mound. A joined pair makes a column. A sliding line makes a curtain. The cave is full of such translations. Movement becomes shape. Chemistry becomes texture. Weather becomes mineral. A curtain may begin at a narrow crack in a sloping ceiling. Water seeps out, but instead of falling immediately, it runs along the underside. Surface tension holds it to the rock for a short distance. As it moves, CO2 escapes. Calcite deposits along the trail. The next water follows the same calcite edge, because that edge is now slightly lower. With each return, the edge lengthens downward. The sheet grows like a folded blade. It may thicken at the bottom, where drops finally gather and fall. Those drops can start tiny stalactites along the curtain's lower edge. They can also feed small deposits on the floor below. Again, one form becomes many. The colors inside a curtain can be especially subtle. Pure calcite may appear white or clear. Iron oxides may add orange, tan, or reddish tones. Organic compounds from soil may contribute faint amber shading. Manganese can darken some surfaces. Clay particles can cloud a layer. Because water chemistry shifts through seasons and routes, these colors can appear as bands. A curtain with bands is sometimes called bacon in casual cave language because of its stripes. The name is earthy, almost too ordinary for such a patient form, but the structure itself remains quiet, layer upon layer. Thin sheets record small changes in what the water carried. When you look at one in imagination, do not rush across its surface. Let the eye follow a single band. It began as a trace dissolved from limestone above. It passed through soil gases, roots, and fractured rock. It reached the cave, moved along a sloping ceiling, and left mineral at the growing edge. Then it stayed. The water moved on. The band remained. Another band covered it, then another. The curtain grew thicker, and the older layer became part of its interior. Every speleothem has this inward direction. The visible surface is only the newest page. Beneath it are earlier surfaces, sealed but still present. This is true of the column, the stalagmite, the flowstone, and the curtain. The cave is layered not only across space, but through each form. At POSTOJNA, the constancy of temperature helps these processes proceed slowly and steadily. The cave air remains cool through the year compared with the changing surface. It does not follow each warm afternoon or cold night. Stone buffers the air. The underground world holds the average rather than the moment. This stability matters for calcite growth. Temperature affects how gases dissolve and escape. It influences evaporation, saturation, and biological activity above. But underground, the smaller variation lets slow chemical balances persist. The cave is not perfectly constant. Air exchange can change with seasons. Water supply can change after rain, snowmelt, or drought. The Pivka River can alter humidity and airflow in connected passages. But compared with the surface, the chamber is calm. It's calm is not emptiness. It is a slow filter. Surface changes arrive below softened, delayed, and transformed. A storm above may not become an immediate change at the drip. It may take time to pass through soil and fractures. By the time that water appears in the chamber, the weather above has already changed. The trees may be dry again, the paths may be quiet, and the sky may have cleared. But underground, the storm is still arriving bead by bead through the stone. This delay is one reason Speleothems can record more than simple rainfall. They do not respond like puddles, filling and emptying in plain view. They respond through storage, filtering, mixing, and the many narrow choices inside Karst. Some water moves quickly through open fractures, reaching the cave after a short passage. Some water lingers in smaller pores, held against mineral surfaces by capillary forces. Some mixes with older water already resting in cracks above the chamber, so one drip may carry a faint blend of yesterday's rain, last month's wet season, and water older still. That blending softens the record, but it does not erase it. It makes the cave less like a clock and more like a slow instrument. The instrument does not strike sharply, it hums. The drip rate may increase after long recharge, but not always at once. The chemistry may shift after soil becomes wet enough for root respiration to rise. The mineral load may change if new water reaches a different seam in the limestone. A quiet cave surface, therefore, is receiving a complicated message in very simple form. The message is a drop. The drop lands. The calcite remains. On the flowstone near the column, this message spreads into thin, pale layers. Each layer is small, but each one belongs to a particular season of water. A wet interval may leave a thicker skin, especially if mineral-rich water arrives often. A dry interval may leave a thinner layer, or may pause growth almost completely. A period of stronger cave ventilation may encourage more CO2 to leave the water. A period of stiller, more carbon dioxide-rich cave air may slow the precipitation of calcite. The shape you see is the result of all these conditions working together. No single cause explains the whole surface. The flowstone is a place where many gentle causes meet. Water supply controls how often the surface is renewed. Carbon dioxide controls how readily dissolved limestone becomes solid calcite again. Temperature helps shape the balance between dissolved gases, evaporation, and mineral saturation. Air movement decides how quickly the wet surface can change chemically. The slope decides where the water goes next. Every condition leaves its own quiet pressure on the final form. This is why the cave's slow breathing matters so much. Air in POSTOJNA does not sit entirely still, even when it feels motionless. It moves through entrances, passages, fissures, and river corridors, often too faintly to notice. The motion may be stronger in some seasons, weaker in others. When outside air is colder than cave air, circulation can change through the system. When outside temperatures become closer to the cave's constant coolness, that exchange may soften. The Pivka River adds its own influence, because moving water affects humidity and air pathways. The river is not beside every formation, but it belongs to the larger cave environment. It helped make the chambers. It still shapes the atmosphere that receives the drops. A speleothem growing far from the river may still be part of that wider breathing system. The cave does not divide itself neatly into separate stories. Its passages are connected by air, water, stone, and the slow memory of flow. On a sloping wall, the flowstone thickens. It does not thicken everywhere at the same pace. The upper part may receive fresh seepage directly from a crack. The middle part may receive water that has already lost some carbon dioxide. The lower part may receive thinner films carrying less remaining mineral. So the surface develops zones. A bright wet track near the top. A smoother, pale sheet below. A ribbed margin where water repeatedly escapes from the main path. A faint, dry edge where older calcite waits for the next season. These small differences make the wall look folded and alive, even though its motion is mineral. The folds are not soft, but they were made by softness. They were made by water obeying gravity in very thin films. A curtain may grow from one of these folds where the ceiling slopes enough to hold water along a line. At first, it is no more than a narrow mineral seam. Then, as water returns, the seam lowers into the open air. The lower edge becomes a delicate ridge. Drops gather there, hanging from the edge before falling. Each hanging drop leaves calcite along the rim, thickening the curtain slightly. Over time, the sheet becomes thin, wavy, and faintly translucent. Its waviness comes from the irregular path of water along the sloping surface. If the water source shifts left or right, the curtain records that shift in its edge. If the flow becomes stronger, the sheet may thicken and extend more quickly. If the flow weakens, the lower edge may dry and pause. A pause is not an ending in a cave. It is only a gap in deposition. The next wet period can return to the same line, adding a new layer over the old. That return may not match perfectly. It may overlap slightly. It may cover only part of the former wet edge. It may bring clearer calcite, or cloudier calcite, or a faint warm tint from trace minerals. So the curtain grows not as a single flat page, but as a stack of slightly different pages. Some are thin and clear, some are milky, some are ambered by iron or organic compounds from the soil above. Some are almost invisible until light passes through them. This is one of the most beautiful secrets of cave formations. Their colors are not applied from outside. They arrive dissolved in water. They come from the path the water took before it emerged. They come from the limestone, the soil, the tiny particles, and the chemistry of the surface world. A pale cream band may mark a time when calcite was deposited cleanly. A rusty line may hint at iron carried from a particular seam. A darker layer may contain more organic material washed from soil. A cloudy zone may form when tiny crystals grew quickly or impurities interrupted their clarity. The curtain does not explain itself aloud, but it holds evidence. It holds water's changing route. It holds the difference between one season and another. It holds the cave's air inside the shape of stone. From farther away, these curtains can seem almost like fabric. They appear to hang from the rock, folded in soft vertical waves. But if you stay with them, they become stranger and calmer than fabric. Fabric is woven quickly by comparison. A curtain of calcite is woven by dripping edges over centuries. Its threads are molecules of calcium carbonate, released from solution and locked into crystal. Its pattern is not chosen. Its pattern is inherited from gravity, slope, and repetition. This is the deeper beauty of Speleothems. They are shaped without intention, and still they seem composed. The cave has no design, yet it produces forms with rhythm. That rhythm comes from water meeting conditions, again and again. The same is true of the flowstones spreading below. Thin sheets build quiet terraces where water pools behind tiny raised rims. Each rim begins when a small boundary slows the flow. Water lingers there, loses carbon dioxide, and deposits calcite along the edge. That new calcite raises the rim a little more. Next time, water pools behind it a little longer. A shallow basin forms, then another forms below it. In this way, a sloping floor can become a staircase of small, shining pools. The pools may be empty in dry periods. They may hold clear water after recharge. Their rims may be smooth as porcelain or rough with small crystal edges. The process is gentle, but it has a built-in consequence. Once a rim forms, it changes the way later water moves. The formation begins guiding the process that grows it. This is why the cave's mineral surfaces can become increasingly intricate over time. A small accident becomes a lasting route. A lasting route becomes a ridge. A ridge becomes a basin. A basin changes the local chemistry by holding water longer against the air. The longer water rests, the more CO2 can leave it. The more CO2 leaves, the more calcite can precipitate, if the water is saturated enough. So the basin grows at its rim, not because anything forces it upward, but because its own shape favors deposition. This is a quiet form of feedback. The cave builds a structure, then the structure teaches water where to build next. Near the column, water may fan across the floor in several paths. One path may form a narrow rib, another may spread into a glossy sheet, another may reach a low hollow and make a small calcite-edged basin. These paths can remain active for years, then fade if the supply shifts. If the feeder crack above changes, the column may become drier on one side. A wet streak may migrate across its surface. The floor below may stop growing where it once received water. Another patch nearby may begin to shine with new moisture. The cave is not fixed, even in its calmest rooms. It is always rearranging which surfaces are active. Some formations grow, some rest. Some are sealed under new layers, some are abandoned by water and left as pale records of an older path. A dry stalactite is not a failed stalactite. It is a completed sentence waiting inside a longer paragraph. A dormant flowstone sheet is not lifeless. It is a surface that once received water and may receive it again if conditions change. This is important because caves hold many timescales at once. A drop forms in seconds. A ring of calcite may take many drops. A straw may require decades to become visible. A stalagmite may grow through centuries. A column may take far longer, if it forms at all. A whole cave system may reflect millions of years of river incision, uplift, and karst development. When you stand inside POSTOJNA, all these clocks are present together. The quick sound of falling water, the slow extension of a mineral tip, the older chamber carved by the river, the ancient limestone that began as marine sediment long before the cave existed. The space is layered in time before it is layered in stone, and the Speleothems bring those layers close enough to see. The flowstone, curtains, and columns are not separate from the cave's atmosphere. They help reveal it. Where air moves slightly more, certain surfaces may grow different textures. Where humidity stays high, mineral films may remain smooth and wet longer. Where air is richer in CO2, degassing may slow, and deposition may shift elsewhere. Where dripping water enters a lower CO2 pocket, calcite may appear more readily. This is why cave scientists pay attention not only to the stone but to the air. They measure temperature, humidity, carbon dioxide, drip rates, and water chemistry. They do this because every formation is part of an active system. But even without instruments, the cave gives sensory clues. A glossy surface suggests recent water. A dry, chalky surface suggests older exposed calcite. A fresh bead at a straw tip suggests an open feeding route. A dark, wet streak on a wall marks a current film of seepage. A pale apron at the base of a column shows where water has spread again and again. The cave can be read visually if the reader is patient. The shapes are sentences. The water is punctuation. The pauses are meaningful too. A long pause in growth may create a boundary inside a formation. Dust, clay, or tiny particles may settle on the surface during the pause. When water returns, new calcite seals that thin interruption inside. Later, a scientist may find it as a faint line. It may mark a drier interval, a change in drip supply, or a shift in cave conditions. The cave does not preserve every year equally. Some intervals leave strong layers. Others leave almost nothing. But the accumulated record can still reveal patterns that are otherwise lost. This is where the story begins to move inward. We have followed water over surfaces. We have watched it build outward, downward, upward, and sideways. Now the same forms ask to be understood from within. A mature speleothem looks still from the outside. Its surface may be smooth, ribbed, wet, or dry. But inside it, hidden from view, are countless former surfaces. Each layer was once the outside. Each one touched cave air. Each one received water. Then it was covered by another layer and became part of the interior. This is a quiet transformation. The present becomes buried without disappearing. The outer skin of a stalagmite is only the newest moment of its life. Below that skin lie older wet seasons, older dry spells, older roots of water through stone. A column's interior may contain the first soda straw, the first mound, and the first sealed contact. A curtain's interior may contain bands from water that moved along the same sloping ceiling ages ago. A flowstone sheet may contain old floor textures sealed under mineral skin. To imagine the interior is to understand that a speleothem is not a solid object in a simple sense. It is a stack of events made solid. Each event is thin. Together, they become landscape. If you could look closely at a cut surface of a stalagmite, you might see bands. Some bands would be clear, with larger calcite crystals arranged cleanly. Some would be milky, with tiny inclusions or finer crystal textures. Some would carry faint color from trace materials. Some would be so subtle that only careful analysis could distinguish them. The bands might curve gently around the growth axis. They might thicken on one side, showing that the drip shifted. They might narrow during a time when less water arrived. They might show a break where growth stopped and later resumed. This hidden structure turns the formation into an archive. Not an archive with pages that can be turned by hand, an archive built from water and sealed by mineral. The cave does not remember as an animal remembers. It remembers by preserving consequences. Rainfall changes chemistry. Chemistry changes calcite. Calcite changes layers. Layers remain. The record is not perfect, but it is patient. A stalagmite may grow in the same place long enough to carry signals from many generations of forest above. It may record shifts in rainfall amount, seasonality, vegetation, and soil carbon dioxide. It may record changes in how water moved through the karst. It may even record periods when growth slowed so much that the surface barely changed. These records are valuable because caves are protected from many surface disturbances. They are dark, they are cool, they are buffered from daily weather. Once a layer forms, it can remain sealed for a very long time. That does not mean every layer is easy to interpret. Water may mix underground, a drip route may change. The same chemical signal can sometimes have more than one cause. But with care, patience, and comparison, scientists can learn from these formations. They do not need to disturb the whole cave. Often they study small samples, chosen carefully from formations where research is permitted. They may use uranium-thorium dating to estimate when certain layers formed. This method depends on tiny amounts of uranium naturally incorporated into calcite as it grows. Over time, uranium isotopes decay into thorium isotopes at known rates. Because fresh calcite usually contains very little thorium at the moment of deposition, the ratio can reveal age. The science is precise, but the idea can be held gently. The stone carries a slow clock inside its chemistry, not a ticking clock, a clock made of atoms changing at a known pace. By measuring those changes, scientists can place growth layers in time. They can say, this part formed earlier, this part formed later. This pause lasted long enough to matter. This interval grew quickly compared with that one. In this way, a stalagmite becomes more than a shape, it becomes a timeline. Stable oxygen isotopes can add another kind of clue. Oxygen in water comes in different forms, including lighter and heavier isotopes. Rainfall can vary in its isotope composition depending on temperature, moisture source, season, and rainfall processes. When calcite forms from that water, it can preserve part of that signal, so the oxygen isotope pattern in a speleothem may tell something about past rainfall and climate. It does not speak simply, and it must be interpreted with care. But it gives the cave another voice. Stable carbon isotopes can also offer clues. Carbon in calcite comes partly from dissolved limestone and partly from carbon dioxide in soil and water. Changes in vegetation, soil activity, water residence time, and degassing can affect the carbon signal. A wetter period may support more soil biological activity, increasing soil CO2. A drier period may reduce soil processes or change how water moves through fractures. Longer residence time in rock may add more limestone-derived carbon. Stronger degassing in the cave may shift the carbon isotope values during deposition. The result is not one simple answer, but a pattern that can be studied. Trace elements add more detail. Magnesium, strontium, barium, and other elements can enter calcite in small amounts. Their abundance may change as water spends more or less time in contact with limestone. They may change if prior calcite precipitation occurs along the route before the water reaches the stalagmite. That phrase means some calcite deposits earlier, in cracks or ceiling surfaces, before the drip arrives. When that happens, the remaining water may become enriched in certain elements. A dry period can encourage this, because water moves more slowly and films may degas before reaching the main drip. A wet period can flush the system more directly, changing the element ratios. Again, the cave records the behavior of water, not just the amount of rain. This is why one speleothem can contain many overlapping signals. Its layers are mineral, chemical, and structural at once. A thick, clear layer may suggest one set of conditions, a thin, cloudy layer may suggest another. An isotope shift may indicate a broader climate pattern. A trace element change may reveal a change in water route or residence time. The cave's memory is not a single line. It is a woven fabric of signals made in darkness. To read it well, scientists compare different evidence. They may monitor modern drips for years, watching how rain above becomes water below. They may measure drip chemistry after storms, through dry seasons, and during snowmelt. They may compare cave air CO2 with surface conditions. They may study several stalagmites from the same cave or region. If several formations show a similar pattern, the signal becomes more trustworthy. If only one formation shows it, scientists ask whether the change belongs to climate or to that one drip route. This careful doubt is part of the patience of cave science. The cave gives records slowly, and they must be read slowly too. A stalagmite may appear simple in the dim chamber, but its meaning depends on many quiet tests. Where did the water enter the rock above it? How long did it remain underground? Did it move through a stable fracture, or did the route shift during wet seasons? Did calcite precipitate before the water reached the growing surface? Was the cave air rich in CO2, or was ventilation strong enough to draw that gas away? Each question narrows the interpretation. Each answer connects the visible stone to invisible movement, and the deeper you listen to the formation, the less it feels like an object standing alone. It becomes a meeting place. Rainfall meets soil. Soil gas meets limestone. Fractures meet open air. Water chemistry meets the still atmosphere of the cave. Then calcite meets calcite, layer after layer, until time has a shape. In POSTOJNA, this matters because the cave belongs to a karst landscape with complex drainage. Water above the cave does not always follow one simple vertical path. It may descend through fissures, travel sideways along bedding planes, pause in pockets, and then emerge far from where it entered. Some routes are quick enough to carry a clear seasonal signal. Others are slow enough to blend many rains into one softened message. A speleothem fed by a quick route may respond strongly after wet periods. A speleothem fed by a slower route may grow more evenly, carrying a gentler record. Neither is better. They simply remember differently. The cave contains many kinds of memory. A fast drip may speak of recent rain. A slow seep may speak of stored water. A flowstone sheet may speak of surface films and air movement. A column may speak of long stability in one place. Together, they form a record that is broader than any single formation. Still, we stay near the one column we have followed, because its story now has an inside. Its outside is pale and damp in narrow streaks. Its base spreads into a smooth apron of calcite. Its upper part disappears into the ceiling where the old stalactite began as a fragile straw. Inside that column, the earliest tube may still be present, buried in later mineral. Below it, the first mound of the stalagmite may also remain, sealed beneath upward growth. The place where they met may be hidden somewhere near the center. It may be only a subtle change in crystal orientation, a small seam, or a band where water behavior shifted. To the eye, the column is whole. To the stone, it is a history of separate stages joined together. This is the quiet reveal of mature speleothems. Their surfaces are smooth enough to suggest simplicity, but their interiors are complex. They are built from thousands upon thousands of moments when water changed its mind chemically. Not intentionally, not suddenly. But each time a drop lost carbon dioxide, the balance moved towards solid calcite. That shift left a trace. The trace joined the previous trace, and the traces became architecture. If you imagine moving into the column, not by breaking it but by thought, the darkness becomes layered. The outermost skin belongs to the latest seepage. Just beneath it lies an older, wet surface, once exposed to cave air. Beneath that is another, and another, each one sealed as the formation thickened. The layers curve around the axis of growth. They bend where water flowed more strongly on one side. They thicken where a wet streak lingered. They thin where the supply faded. They may include tiny pauses, where dust or clay settled before growth resumed. These pauses matter. They are not blank spaces. A pause can mark a dry interval, a blocked route, or a change in ventilation. When water returns, it covers the pause with new calcite. The interruption becomes a line inside the stone. A line can be dated, A line can be compared with other lines. A line can tell the scientist that the cave was not always growing at the same pace. But the cave never hurries to explain itself. It offers only mineral evidence. The rest requires careful listening. Uranium-thorium dating can give an age to certain layers, but the age is part of a larger story. Stable isotopes can suggest changes in water and carbon, but they must be checked against modern conditions. Trace elements can show how water moved through rock, but they can also reflect earlier calcite deposition along the route. The most reliable understanding comes when several clues lean in the same direction. A thick growth layer, a shift in oxygen isotopes, and a change in trace elements may together suggest a wetter period. A thinner layer, more evidence of prior calcite precipitation, and altered carbon values may suggest slower seepage or drier conditions. But even then, the interpretation remains humble. The cave is old, and its pathways are hidden. Scientists learn from it by accepting that certainty grows slowly. This humility suits the cave. POSTOJNA does not reveal itself all at once. Its passages curve away into darkness. Its water disappears and returns through unseen channels. Its mineral surfaces appear still, while chemistry continues at their edges. The more you understand, the quieter the cave becomes. Not empty quiet, a dense quiet full of causes. The drip we followed began as rain, but by now it has become evidence. It has made a straw, it has made a stalagmite, it has joined into a column, it has spread into flowstone, it has laid down bands that may one day be read as signs of older weather. The same water path has moved through visible forms and hidden records. This is why the chamber feels so complete, even though it is unfinished. Every shape is both a result and a beginning. The column is a result of long vertical growth. Its wet side is a beginning for new flowstone. The flowstone is a result of thin sheets of water. Its lower lip may become a beginning for new drips. A curtain is a result of water sliding along a sloped ceiling. Its lower edge may become the beginning of small stalactites. A stalagmite is a result of falling drops. Its growing layers may become a beginning for future climate memory. The cave is not moving toward one final form. It is rearranging process into form, and form back into process. There is a kind of peace in that. Nothing is wasted, because every path leaves some consequence. Even water that deposits no visible mineral still changes the system slightly. It may humidify air. It may carry dissolved material onward. It may rinse a surface. It may feed a lower seep. It may join the hidden drainage that eventually belongs again to the Pivka river system. The cave is connected by more than visible passages. It is connected by moisture. It is connected by chemistry. It is connected by tiny pressure differences and slow air exchange. It is connected by limestone itself, fractured and soluble and patient. When you look at the column again, the idea of a single object becomes too small. It stands in the chamber, but it also reaches upward into the forest through its water source. It reaches downward into the floor through its mineral apron. It reaches sideways through films of water that move across flowstone. It reaches backward into older climates sealed inside its layers, and it reaches forward because its wet surfaces are still receiving new calcite. This forward direction is quiet. It does not announce itself. A fresh layer may be so thin that the surface only looks slightly brighter. A new bead may gather near the base and leave a faint rim no wider than a thread. A wet patch on the ceiling may begin a soda straw too small to notice. Yet these small starts are the cave's future. After one form matures, new beginnings appear nearby. That is the next movement in the chamber. Not a conclusion, but a spreading of attention. The column has changed the old drip path, and that change has opened other paths. Water that once fell through air now travels along stone. Some of it reaches the base. Some of it spreads across the floor. Some of it follows a hairline groove toward a lower hollow. Some of it gathers on a tiny projection where it may hang for a moment before falling. Every division of the water creates a possibility. A new drip point may begin beneath an overhang of flowstone. A small rim may grow around a shallow pool. A faintly wet ceiling patch nearby may begin its own calcite ring. The cave does not stop building because one column is complete. Completion, here, only changes the distribution of water. This is the aftermath of formation. A mature speleothem becomes part of the conditions that make younger ones. Its shape redirects films. Its surface changes airflow on a very small scale. Its base alters how water spreads across the floor. Its presence can shade nearby surfaces from direct dripping while feeding others. The old formation becomes landscape for the next formation. This is a slow version of succession, but mineral rather than biological. One surface prepares another. One route closes, another opens. One deposit becomes the foundation for later mineral skin. The chamber keeps adjusting. If you settle lower now near the calcite floor, the world becomes even more detailed. The floor is not flat. It has soft rises, shallow hollows, thin crusts, damp seams, and patches where sediment gathers. Some areas are hard, pale, and polished by mineral films. Others hold fine clay, washed in during wetter periods and left where water slowed. Some small stones may be rounded by old movement. Others are coated in calcite, made softer in outline by repeated seepage. The floor is the place where falling water finishes one journey and begins another. A drop may land on bare calcite and spread. It may land on sediment and sink. It may land in a shallow basin and join clear water already waiting there. It may carry enough dissolved calcium carbonate to leave a trace, or it may arrive undersaturated and dissolve a little instead. Even deposition is not guaranteed. If the water still holds enough carbon dioxide, or if conditions shift, it may carry mineral onward. A cave is not only a place where stone grows, it is also a place where stone can be removed, softened, or reworked. But in the quiet chamber we are following, the balance has favored deposition for a long time. That is why the surfaces are pale. That is why the column stands. That is why flowstone spreads in glossy sheets across the lower slope. The cave has been receiving more calcite here than it has lost. This balance can change. A new water route could bring less saturated water. A shift in air CO2 could slow precipitation. A stronger flow could wash sediment across the floor. But for now, the chamber remains a place of gentle accumulation. The drip field continues. Not one drip now, but many. Some are steady. Some are rare. Some are active only after recharge. Some have been quiet for years, leaving dry tips behind. Each one has its own little territory on the floor. A steady drip may build a small bump. A wandering drip may make a lopsided patch. A line of seepage may grow a curtain. A sheet of water may extend flowstone over older forms. The cave floor is a map of these territories, though their borders are not fixed. After heavy rain above, a dry point may wake. After a long dry interval, a steady drip may slow until the sound disappears. The cave's activity shifts softly with the surface. You can hear it if everything else is still. A drop falls from a distant ceiling, then another, from somewhere behind the column. Then a faint patter where water reaches a shallow pool. Then silence again. The rhythm is uneven because the routes are different. One drip may be supplied by a fracture that fills quickly. Another may depend on water stored in smaller pores. Another may continue long after rain has ended, fed by slow release from the limestone. Each sound is a different travel time. The chamber is listening to the surface through stone. This is a gentle way to understand Karst. It is not only caves and sinkholes and underground rivers. It is a landscape where water decides its route through soluble rock. On the surface above POSTOJNA, rain may vanish into cracks rather than forming long streams. Soil may be thin, limestone may lie close beneath roots. Water may descend quickly in some places, slowly in others. Underground, the routes join, separate, and rejoin. The visible cave is only the open portion of a much larger plumbing system. Speleothems form where that hidden plumbing meets air. They are the visible edge of invisible drainage. A stalactite marks a place where seepage reached an open void. A stalagmite marks where the falling water regularly touched the floor. A column marks where that relationship endured long enough to close. Flowstone marks where water became a film. Curtains mark where it traveled along a slanted line before dripping. Each form is a shape, and each shape is an explanation. The explanation begins with water, but it depends just as much on air. If the chamber were completely filled with water, these air-grown forms would not develop in the same way. The drop needs open space to hang. Carbon dioxide needs a place to escape. Calcite needs a surface where saturation can shift. The presence of air changes the chemistry. This is why speleothems often grow after passages become partly or fully air-filled. The Pivka River and earlier underground flows carved the space. Later, when conditions allowed open air and dripping, calcite could begin returning. The cave's history is therefore divided by water level and airspace. First, water removes limestone and enlarges passages. Then, where air occupies the void, mineral-rich water can drip and deposit calcite. The cave is shaped by both absence and addition. A passage is made by what water takes away. A speleothem is made by what water gives back. That exchange continues around you. In a low hollow near the column's base, pale sediment gathers. Some of it may be clay washed from fractures. Some may be fine limestone particles. Some may be tiny broken crystals from older surfaces. Some may be material carried during past wet intervals, when water moved across the floor more strongly. The sediment rests because the water slows there. Still water lets fine particles settle. Later, calcite may coat them, binding them gently into the floor. A hollow filled with soft sediment can become sealed beneath a flowstone's skin. Inside that sealed place, the cave preserves another kind of record. Not the clear banding of a stalagmite, but a quiet deposit of particles. Sediments in caves can tell of old floods, slow pools, or changes in flow. They may contain grains from outside the cave. They may include mineral fragments from the limestone. They may be sorted by water movement, with heavier grains left in one place and finer clay carried farther. In the chamber of speleothems, sediment is often subdued, tucked into hollows and covered by calcite. But it belongs to the same story. Where water is energetic, it can move grains. Where water is slow, it can drop them. Where mineral-rich films pass later, they can seal them. The floor becomes a layered meeting of sediment and calcite. This layering matters because speleothem growth is not always continuous. A stalagmite can grow over sediment. Flowstone can cover a mud surface. A drip can shift onto an older deposit. A calcite layer can protect sediment from later movement. Then a later change can expose part of it again. The cave floor is revised gently, not erased all at once. One surface is laid over another. A patch of old clay becomes hidden beneath pale mineral. A broken edge is rounded by new growth. A hollow becomes a basin. A basin becomes rimmed with calcite. A rim changes the direction of future water. This is the slow rearrangement of the chamber after the column. The main vertical story has changed. Now the floor receives water in new places. Nearby ceilings begin their own small points of activity. A bead gathers on a dark patch of limestone not far from the old column. It is not yet a straw. It is only a wet place where seepage has begun to emerge. Perhaps the old route was partly blocked by calcite. Perhaps pressure in the fracture system shifted after wet seasons. Perhaps water found a neighboring microcrack that offered less resistance. The reason may be small, but the consequence could last. If this bead returns often enough, a new calcite ring will form. The first ring will be almost invisible, then a lip, then a hollow tube. The cave begins again. This is not repetition in the empty sense. It is the same process under slightly different conditions. The new drip is located a little to the side. The ceiling texture is different. The floor beneath may be sloped rather than flat. The cave air near it may circulate differently because the column now stands nearby. The water chemistry may differ because the route through the rock is not the same. So the new formation will not copy the old one. It will be related, but distinct. It may become a short straw, then dry. It may become a delicate stalactite, but never build a stalagmite below. It may fall onto a sloped flowstone surface and spread rather than mound. It may feed a tiny basin at the floor. The future form depends on the behavior of water, and water is guided by conditions. This is why the cave never produces exact duplicates. Even when the chemistry is similar, the route is never exactly the same. A few centimeters of position can change the drip height, a rougher floor can change splash, a slight air movement can change degassing. A different fracture can change mineral load, a little clay can cloud the calcite, a trace of iron can warm the color. The cave's variety comes from small differences being preserved over long time. At the new drip point, The first bead grows. It hangs from the ceiling, round and clear. The chamber around it remains dim. The older column stands nearby, thick and pale, already joined from roof to floor. The flowstone apron spreads below, smoother where films have passed often. The new bead reflects all of this in miniature, though only for a moment. Then it falls. Its sound is faint because the floor is damp. Perhaps it lands on calcite, perhaps on a thin skin of sediment. Either way, it has begun marking a place. One fall means little. Many falls mean form. That is the simplest law of this quiet chamber. One drop can be invisible. Many drops can build a world. Above the ceiling, rain is still passing through the karst. Some of it has moved through soil rich in CO2. Some has dissolved limestone along narrow pathways. Some has mixed with older water stored in cracks. Some has already deposited calcite before reaching the open cave, changing what remains in solution. When the water appears at a new ceiling point, it carries a history too small to see. The bead is transparent, but not empty. It holds dissolved ions. It holds carbon from soil and rock. It holds oxygen from rain. It also holds a little trace of the path it took, a chemical memory of darkness before the cave. That memory is not visible as the bead hangs from the ceiling, but it will matter if the drip returns. If enough water follows the same tiny opening, the bead will become a habit. A habit in a cave can become stone. The new drip falls near the edge of the older flowstone apron, where the floor is not level. Instead of landing on a flat patch, it strikes a shallow slope and spreads slightly downhill. This changes the outcome from the very beginning. A drop falling on level stone may build a mound, but a drop falling on a slope begins to travel. It leaves part of its mineral load near the impact point, then carries the rest a little farther. A faint streak begins below the landing place, darker when wet, paler when dry. At first, the streak is only moisture. Then, after many arrivals, it becomes a narrow ribbon of calcite. The new formation does not rise upward in a simple answer to the ceiling, it stretches. It follows the lean of the floor, as if the floor itself is teaching the water where to go. This is one reason the aftermath of a column is never simple. Once water has been redirected, it meets surfaces that are already shaped by older growth. The new drip lands on inherited ground. It is not beginning in an untouched chamber. It is beginning on a surface made by previous water, previous calcite, previous pauses, and previous returns. That inheritance changes everything. A tiny ridge of old flowstone may divert the fresh film to one side. A rough patch may slow it enough for more carbon dioxide to escape. A smooth, glazed area may let it pass with little deposition. A speck of clay may remain trapped beneath a new clear skin. The floor becomes a quiet argument between the old shape and the new water. Neither wins quickly. They adjust to one another. Over months, the wet track may become more reliable. Over years, it may become visible even when dry. Over centuries, it may thicken into a raised vein across the floor. The same water that might have made a stalagmite now makes a low, spreading form. The cause is not mysterious. It is the slope. It is the landing point. It is the amount of water in each drop and the chemistry it carries from above. It is also the cave air which receives CO2 from the water whenever the film spreads thin. A wider film gives the gas more surface through which to leave. As CO2 escapes, calcium carbonate becomes less able to remain dissolved. Calcite returns, not as a point, but as a skin. It may be less than the width of a hair for a long time, but it smooths the floor just enough to guide the next film. This is how the new path becomes self-reinforcing. Water lays down a surface, then later water follows that surface. Then the surface thickens. A small consequence becomes a root. The root becomes a form. The form becomes part of the chamber's future. Nearby, another new bead appears on the ceiling, but its behavior is different. It forms slowly, swells, and remains hanging for a long time. The feeding route above it is weaker, perhaps only active after long rain. When it finally falls, the drop lands several hand-widths from the flowstone track. The sound is sharper because the surface beneath is drier and harder. One drop marks the place, then nothing follows for a while. This is a quieter kind of beginning, one that may never become large. Many possible speleothems begin and pause before the eye can recognize them. The cave is full of attempts that are not failures. A drip may not last long enough to build a straw. A wet patch may dry before the first ring becomes stable. A narrow film may dissolve part of an older surface instead of depositing new calcite. The system keeps testing paths because water is always searching through the rock above. Some paths persist, some vanish, some return after years of silence. This irregularity is part of the record. A chamber with many small, inactive tips tells of roots that once carried enough water to build. A dry straw hanging from a ceiling may mark an older wet interval. A tiny mound on the floor may show that a drip once landed there, even if the ceiling above is now quiet. The absence of water is also evidence. It says the root changed. It says the chemistry shifted. It says the cave has moved on, at least for now. The older column remains the largest form in this small field of activity. Its surface is not uniform. One side is dry and softly matte. The other side carries a dark, wet line that descends in a slow curve. The wet line does not fall straight because the column is not smooth at the microscopic scale. It has ridges, crystal faces, tiny ledges, and old-growth seams. The film catches on these details. It pauses, it widens, it narrows again. At every pause, the water has more time to exchange gas with the air. At every narrowing, the film may move more quickly and carry some dissolved material farther down. The result is a streak with texture. A little more calcite gathers along one edge than the other. The wet side of the column slowly becomes ribbed. The dry side remains closer to its older surface. This uneven growth may eventually shift the column's shape. It may thicken in one direction. It may develop a soft shoulder where water repeatedly leaves the same route. It may build a small knob near the base, where flow slows before spreading onto the floor. The column is still becoming, even though its most visible event, the joining of ceiling and floor, has already happened. This is the important consequence of the story so far. Completion did not stop the process. It changed the conditions. Once the drop no longer fell freely, water gained a longer path in contact with calcite and air. That longer path allowed deposition along the side. The side fed the base. The base fed flowstone. The flowstone now guides new films outward into the chamber. The original drip has become a small watershed of mineral water. It is not large, but within the scale of a cave, it is meaningful. A single stable route from the surface has reorganized a patch of underground landscape. The ceiling, the column, the floor, and nearby hollows all feel its influence. This is how karst chambers accumulate complexity. They do not need a single great event. They need connected small events, repeated under slightly changing conditions. The drip changes the stalactite. The stalactite changes the falling water. The falling water changes the stalagmite. The stalagmite changes the splash. The joined column changes the flow. The flow changes the floor. The floor changes the next path. The chain is gentle, but it is exact. If you were to trace the water after it reaches the floor, you would find that even its departure matters. Some of it evaporates only a little, because the cave air is humid. Some of it seeps into fine cracks in the calcite floor. Some of it collects in shallow basins. Some of it moves toward lower passages, joining other thin films and seepage lines. Eventually, part of this water may enter the broader underground drainage. It may find its way toward the Pivka River system or toward hidden channels beyond the chamber. By then, it may have lost much of the calcite it once carried. Or, if conditions change, it may dissolve a small amount again. Karst water is not always depositing. Its behavior depends on its balance with CO2, calcium, bicarbonate, and the surfaces it meets. If water becomes undersaturated with respect to calcite, it can dissolve stone. If it becomes supersaturated, it can deposit. In the same cave, both can happen in different places. A drip can build a stalactite at the ceiling, then still carry enough mineral to build below. Another flow can pass over older calcite and remove a faint amount from the surface. The cave is not simply growing, it is being adjusted. In the chamber we are following, the overall feeling is one of accumulation. But even accumulation includes small dissolutions, tiny rearrangements, and changes in texture. A glossy flowstone surface may be polished by repeated wetting. A thin edge may be softened where water remains slightly aggressive. A crystal face may be coated, then partly etched, then coated again. These changes are subtle. They do not disturb the calm. They make the calm more truthful. The cave is still because its motion is slow, not because nothing happens. Near the low hollow, a thin film of water pauses after a wetter season. It fills a shallow depression behind a calcite rim. The pool is clear enough to reveal the pale floor beneath. Its surface is so still that the ceiling appears faintly inside it. Along the rim, water touches air, calcite, and the edge of the basin all at once. This contact encourages more deposition at the boundary. The rim grows more than the floor of the pool. That makes the basin slightly deeper. Next time water arrives, it can hold a little more. A little more held water means a little more time for CO2 to leave. That means a little more calcite can gather along the edge. The basin builds the condition that builds the basin. This is a quiet loop. It can create small terraces, one below another, if water overflows from each rim to the next. In some caves, these terraces become delicate fields of rimstone pools. In POSTOJNA, where conditions vary across passages, some pools may be active and shining, while others are dry and pale. A dry rim still records old water. Its curve shows the former edge of a pool. Its height shows where water once lingered long enough to deposit mineral. Its texture may show whether growth was smooth, crystalline, or interrupted by sediment. Even without water, the basin speaks. But when water returns, the old rim becomes active again. It does not have to start over. It receives the new film on a surface already prepared by older deposition. This is why some formations can grow episodically for very long spans. They may pause through dry intervals, then resume on the same edge when recharge returns. The cave does not erase the pause. It covers it. Inside the rim, a thin boundary may remain where dust settled during dryness. That boundary may later become a line in the stone. A line like that can be read if someone studies it carefully. It may say that the basin once stood dry. It may say the water supply shifted away. It may say that cave air changed enough to slow deposition. The exact meaning depends on context, but the line exists because the cave had a pause. In the larger story, pauses are as important as growth. They break the sequence into chapters. They show that the system breathes unevenly. They make speleothems into records rather than simple accumulations. The new drip near the Flowstone edge begins to show its own pauses. After a wet season, it falls regularly for several weeks. The ceiling tip stays bright. The floor track stays glossy. A narrow calcite film spreads downhill and dries with a faint sheen. Then, as the surface above becomes drier, the interval between drops increases. The bead takes longer to form. The wet streak on the floor fades. The calcite surface becomes matte again. For a time, the formation rests. This rest does not undo the thin layer already deposited. It simply leaves it exposed. Dust from the cave air may settle on it. Tiny clay particles may remain where the final films evaporated. The surface may develop a slightly different texture because it dried slowly. When water returns, the next layer will not be deposited on a neutral surface. It will cover the evidence of the pores. This creates structure inside even the smallest flowstone track. From the outside, the track may look like a simple pale line. Inside, it may contain alternating layers from wet pulses and dry intervals. The cave keeps small calendars in places the eye overlooks. A large stalagmite may be easier to study because its layers are thicker and more continuous. But a thin flowstone skin can also carry records of change. Its layers may be too fine to separate without careful tools. Its growth may be irregular. Its chemistry may reflect films moving across older calcite rather than direct dripping. Still, it belongs to the same archive. Water arrives, conditions decide what remains. Mineral preserves the decision. This is the deep simplicity underneath all the complexity. The specific tools of science can measure the layers, but the basic process is visible in the chamber. Where the surface is wet, change is possible. Where water loses CO2, calcite may grow. Where flow pauses, sediment may settle. Where roots shift, growth moves. Where conditions stay faithful, forms become large. Everything follows from those relationships. The chamber after the column is therefore not an ending, it is a field of consequences. The joined form stands as a record of long stability, while the surrounding floor shows younger changes. The new drip on the slope begins a spreading track. The intermittent drip on the dry patch marks a possible future mound. The basin rim thickens when water returns. The column's wet side grows ribs. The old flowstone apron smooths the low ground and carries water farther than before. Each of these changes is small. Together, they make the cave more layered. In time, the new track may merge with the older apron. If it does, the boundary between old and new flowstone may disappear from the surface. Water will glide across both. Calcite will cover the seam. Only the interior will remember where one phase ended and another began. This kind of hidden boundary is common in caves. Surface continuity can conceal internal change. A smooth sheet may contain separate growth episodes. A column may contain a straw, a stalagmite, and a sealed meeting point. A curtain may contain many alternating bands from shifting water chemistry. A floor crust may cover sediment, older calcite, and small fragments of fallen rock. The cave looks unified because later water softens the joins, but inside it is assembled from events. This matters because what seems timeless is often very precisely timed. A speleothem may include layers that formed quickly, then a gap lasting centuries, then slower growth again. Another may grow steadily through long intervals, preserving fine annual or near-annual bands under favorable conditions. Some may stop altogether when the water route changes. Others may reactivate after a long sleep. The cave is full of different tempos. You can sense them by looking at the forms. Thin straws suggest steady, delicate dripping. Broad stalagmites suggest repeated impact and spreading. Columns suggest long alignment. Flowstone suggests films. Curtains suggest water traveling along slanted edges. Rimstone suggests pooling and overflow. Each form is a tempo made solid. The POSTOJNA Caves hold these tempos within a large, river-shaped system. The Pivka River did not make each calcite fold, but it made the architecture where those folds could grow. It opened passages through limestone. It carried sediment. It changed levels over time as the karst evolved. It left air-filled chambers where seepage from above could become visible. Without that larger hollowing, the drip would have no open space in which to fall. Without later seepage, the open space would lack the pale mineral forms that now soften it. The cave's beauty comes from this sequence. First removal, then return. First, the river makes absence, then the drip gives shape to the absence. This is a slow balance between loss and addition. It is also a balance between surface and underground. Rain begins above, in weather and forest. Limestone receives it, the cave reveals it. The river carries some of it onward. No part is isolated. Even the quietest bead on the ceiling is connected to the whole karst. If the forest soil above changes its moisture, the drip may change. If the amount of CO2 in the soil air changes, if the fracture route shifts, the mineral chemistry changes. If cave ventilation changes, the rate of degassing changes. If the Pivka River alters humidity in connected passages, nearby deposition may respond. The Speleothem is therefore a meeting point for the landscape. It is not separate from rain. It is not separate from roots. It is not separate from the river. It is not separate from the air that seems so still. The cave gathers all these influences into calcite. That gathering can feel almost tender because the forces are ordinary. Rain, soil, stone, air, time. No single part is dramatic, but together they make forms that can outlast almost everything visible above them. A surface tree may grow, fall, and decay, while a stalagmite adds only a small thickness. A footpath above may vanish under leaves, while a calcite layer remains sealed underground. A wet century may leave a measurable band. A dry interval may leave a pause that becomes a line. The cave keeps what the surface cannot keep, not every detail, not every storm, but enough to preserve the slow character of change. This is why the interior of a speleothem can be studied like a climate archive. The layers are not simply beautiful, they are evidence of how water moved through the landscape at different times. Uranium-thorium dates can anchor the sequence. Oxygen isotopes can suggest shifts in rainfall or temperature patterns. Carbon isotopes can hint at soil activity, vegetation, degassing, and water residence time. Trace elements can point toward changes in rock interaction and prior calcite precipitation. Layer thickness can show growth rate changes. Crystal texture can reveal shifts in saturation and flow. All of these clues are strongest when they are read together. One signal alone may be ambiguous. Several signals, aligned carefully, can make the past clearer. Still, the cave asks for restraint. A formation is not only a sample, it is part of a living mineral system, still receiving water, still altering its surface. Scientists choose carefully when they study speleothems. They may sample broken pieces already detached where possible. They may take small cores from selected forms with permission and purpose. They may monitor active drips rather than disturb large formations. They may compare modern water chemistry with ancient layers. The goal is not to take the cave apart. The goal is to listen without silencing the thing being heard. That kind of care matches the pace of the place. In the chamber, the new drip continues after another rain. The bead forms more quickly now. Water must have reached the ceiling root with less delay. Perhaps the fractures above were already wet, and new rainfall pushed stored water downward. Perhaps a larger network of cracks became connected during recharge. The drip interval shortens. The floor track darkens. A second narrow wet line branches from the first, because the growing calcite skin has altered the slope. This branch is important. It means the formation has started redirecting its own supply. The first layers smoothed one path, but also raised a tiny edge. Water now divides at that edge. One thread continues along the older groove, where the surface is already smooth and slightly lowered by wetting. The other slips to the side, onto a drier patch that has not received much mineral before. At first, the side branch carries little water, only enough to darken the calcite for a few minutes after each drip. But that is enough to begin a choice. Where the branch slows, it leaves a faint line of new calcite, and the line becomes a guide for the next arrival. The floor is no longer simply receiving the drip, it is organizing it. This is the small final escalation in the chamber, the moment when one completed formation begins shaping several unfinished ones around it. The column above has already closed the old vertical distance. The flowstone at its base has already spread the water outward. Now the younger skin is dividing the film into separate paths, each one capable of becoming its own record. One path may thicken into a rib, another may fade when the next dry season comes. A third may reach a shallow hollow and begin raising a little rim around it. This is how a cave floor becomes complicated without ever becoming loud. The evidence is in the surface. The newest wet line shines more brightly than the older calcite beside it. Its edge is sharp in places, soft in others, because deposition is not yet even. A tiny grain of clay rests at one bend, caught where the water slowed. Below it, the film spreads thinner, and the calcite becomes smoother. A few centimeters farther on, the water loses its shape and vanishes into a pale, matte patch. That vanishing is not failure. It means the film has lost enough volume, or enough mineral, or enough momentum to stop building visibly there. The active edge remains higher up, nearer the branch point, where water still arrives with strength. In time, this place may become a low fork in the flowstone, a mineral delta on the cave floor. It is not a river delta in size, but the idea is related. Flow divides. Sediment, or in this case calcite, gathers where movement slows and spreads. The form grows outward from the balance between supply and surface. The cave repeats large landscape principles in small underground gestures. Above POSTOJNA, valleys and karst depressions guide rain toward hidden roots. Below POSTOJNA, ridges no taller than a fingernail guide films of mineral water across the floor. Scale changes. The logic remains. Water follows the easiest path, then alters that path by moving through it. The new branch now changes the old track as well. Because some water has left the main groove, the older line receives slightly less flow. Its surface may dry sooner between drops. Its growth may slow. The side branch, newly active, may receive enough water to brighten after every recharge. A shift too small to notice in one season becomes visible over longer time. The cave redistributes its attention. This is the consequence of the column. carried outward into the floor. One joined form has changed the hydrology of a small chamber. The word hydrology may sound large for such a quiet place, but it belongs here. Hydrology is not only rivers, floods, and springs. It is also the path of a bead over calcite, the waiting time between drips, the way a damp streak chooses one side of a ridge. In Karst, the smallest water paths can leave the longest records. The older column stands above this branching floor, pale and still. Its wet side darkens during recharge. Its dry side holds the memory of earlier layers. At its base, a faint knob has begun to grow where the descending film slows before spreading outward. That knob is a new accumulation point, made by the column's own surface. It may thicken over centuries into a rounded bulge, or it may remain only a slight swelling if the water shifts again. Nothing here is guaranteed except change at a slow pace. The cave's future is conditional. If rain continues to enter the same fractures, the branch may lengthen. If soil CO2 remains high enough, the water may keep carrying dissolved limestone. If cave air allows steady carbon dioxide loss, calcite will continue to return. If the root clogs, dries, or diverts, the active line will pause. Every formation is a sentence begun under conditions that may not last. This uncertainty gives the stillness its depth. The cave looks finished because the eye cannot see the next fraction of growth. But chemically, the chamber is unfinished everywhere. Moisture remains. A bead may be gathering above a ceiling point that has never built a visible straw. A rim may be growing around a pool too shallow to notice. A cloudy film may be sealing clay beneath a flowstone skin. A dry tip may be waiting for a wetter season to wake again. The cave is full of almosts, almost a stalactite, almost a curtain, almost a column, if the drip holds its place long enough. These beginnings are quiet, but they are not empty. They are the way the cave keeps time open. Near the floor, the low hollow receives the last of the divided film after a wet interval. The water gathers there as a thin, clear pool, barely covering the calcite beneath. It holds still. At its edges, the surface tension draws a curved line against the rim. Along that line, carbon dioxide leaves the water a little more easily. Calcite settles there, crystal by crystal, raising the rim by an amount too small for the eye. The center of the pool changes less. The edge grows, so the hollow becomes more defined because water lingers where earlier water made room for it. This is the cave's slow feedback, returning one final time. A form receives water. The water changes the form. The changed form receives water differently. From that loop, the chamber gains detail. In the same quiet way, the new branch on the floor may one day create its own rim. The intermittent drip may one day build a low mound. The column may thicken on its wet side until the old seam of joining lies deeper inside. The original soda straw, if it still exists within the column, will remain hidden, a small hollow memory at the center of later stone. It began as a ring, no wider than a breath. Now it belongs to a structure that has redirected water across the chamber. That is the payoff of the whole descent into this process. A single drop did not merely fall. It traveled through forest soil, dissolved limestone, reached cave air, released CO2, and left calcite behind. It built downward, it built upward, it closed a distance. It changed the route of later water. It became part of a larger mineral landscape, where every surface is both record and cause. The POSTOJNA Caves hold this lesson gently. The largest passages remind you of the Pivka River and of the water that removed stone to make space. The Speleothems remind you of the seepage that returned stone to that space, grain by grain, ring by ring, skin by skin. Together, they show that a cave is made by subtraction and addition at once. Limestone dissolves, calcite precipitates, water leaves the rock, then gives some of it back in a new shape. The chamber around the column is the aftermath of that exchange. It is not the end of formation. It is the place where an old formation has become terrain for younger processes. The floor is damp in some hollows, dry in others. The air is cool and nearly still. Pale calcite catches the faintest light, while darker wet tracks show where the most recent water has passed. Fine sediment rests in low places, waiting either to be moved or sealed. The column stands quietly in the center of its small field of influence. Above it, unseen fractures continue upward through the limestone. Above those fractures, soil holds roots, microorganisms, fallen leaves, and pockets of carbon dioxide-rich air. Above the soil, rain will come again. Some rain will run elsewhere. Some will enter the karst, some will pause in stone for days, months, or longer. Some small portion may find the old root, or a newer one beside it, and appear at the ceiling as a clear bead. When that bead reaches open cave air, the same delicate exchange will begin. CO2 will leave the water will become less able to hold all the calcium carbonate it carries. Calcite will form at an edge, a tip, a rim, or a thin film. The change will be almost invisible, but it will be real. That is the deep patience of Speleothems. They do not need to be seen changing in order to change. They only need the conditions to return. Rain, soil, limestone, air, and time. These are the quiet instruments. The cave is the place where they play slowly enough to become stone. Now the chamber settles into its final stillness. The newest branch on the floor is drying. The wet shine withdraws from its lower end first, leaving a pale trace behind. The bead at the intermittent ceiling point has not yet returned. The pool in the hollow is motionless. The column remains damp along one narrow side, where a film descends so slowly it seems not to move at all. If you listened for a long while, you might hear one drop fall somewhere beyond the light, then another, then nothing. In that nothing, the processes continue beyond hearing. Water is still moving through the rock above. Carbon dioxide is still dissolving into rainwater in the soil. Limestone is still being carried molecule by molecule toward dark openings. Somewhere nearby, a ring of calcite may be forming too small to name. Somewhere else, an old surface may be resting through a pause that will last longer than memory. The POSTOJNA Caves remain unfinished. Their forms are ancient, but not final. The column has closed one distance, yet opened many quieter beginnings around it. The floor has received the water, divided it, slowed it, and kept a faint record of its passing. The chamber holds the result without announcement. Pale stone, cool air, a few wet lines, a silence measured by drops. And at the edge of the newest calcite branch, where the surface has only just begun to rise, one last bead gathers in the dark, carrying a little dissolved limestone toward a shape that has not decided what it will become.